So in previous videos, we've learned about transformations. We've learned about translations, or what we call slides. We've learned about rotations, which are where you spin a shape. And we've learned about reflections, which is where you flip a shape over a certain line of reflection. Well, in this video, what we're going to learn about is a new kind of transformation called dilations. And dilations have one key difference from the other three transformations that I just mentioned. There's one big difference between a dilation and a translation, a rotation, or a reflection. So let's jump right in and take a look. So first off, let's go ahead and define what a dilation is and the notation that we're going to use for it. So it says a dilation is a transformation that has a center of dilation at C, and C will be a point, and a scale factor of n, where n is something bigger than 0. Right? So this notation here that we see, big capital D with a little subscript parentheses, n and c. N is something called the scale factor. We'll learn what that means in a minute. And C is what we call the center of dilation. And that will always be a certain point on the plane. And that number n, it says, always needs to be something bigger than 0. And we'll find out what the different values of n would tell us about our dilation. So let's take a look at some of the properties of what a dilation is. So if we have, let's say, this segment right here, segment XR, and we're going to dilate that using C here as the center of dilation, what exactly is going to happen to this? Well, the way it's worded out here is a little bit tricky. It says that point R will map to R prime in such a way that R prime is on ray CR, and the distance from C to R prime is n times the distance from C to R. That's kind of what that is saying. Now let me try and break that down a little bit into some language that's a little bit easier to understand. So you have let's just concentrate on point R right here. We're going to dilate point R. What essentially we're going to do is we're going to connect our center of dilation to that point, and we're going to make this ray right here. And think of that as like a rail that point R can slide back and forth on, right? So point R can slide on that rail. The dilation of point R is going to slide, if it's going to slide to a point that is n times CR distance away from C. Now, so what does that mean? Well, let's suppose that this distance from C to R was, I don't know, let's say this was 2 units away. And we were going to do a dilation of let's say, 1.5. Let's say n was going to equal 1.5. Then that means that R, so C to R, is equal to 2. C to R prime will equal 1.5 times 2, which would be 3. So this distance from C to R prime would be 3. And then that same pattern would hold true for any other points that are getting dilated according to this same rule, right? So we notice here that if we were actually dilating this entire segment XR, well, R gets moved 1.5 times away from C compared to where it is now. So if it's 2, it gets moved 1.5 times 2, which is 3. It gets to move to a spot that's 3 units along this rail. It gets kind of slid over along that rail. We make another rail connecting C to X, and then whatever this distance is, all right, let's just say that distance is D, then the distance from C to X prime is 1.5 times D. All right? Each length in the image, so this is, remember, the wording that we use is we start with our pre-image, segment XR, and our image is what we get after we do the transformation, so that would be like X prime, R prime. Any length that's in the image is going to get multiplied by n in the pre-image. Or sorry, any length in the pre-image is going to get multiplied by n in the image. So let's say that this length here, XR, let's suppose that was 1 unit in length. Well, then the length of, if XR equals 1, then X prime R prime is equal to 1.5 times 1, or in this case that would be 1.5. So that's kind of the first, those two properties are really the basis of what a dilation does, is it takes a point and it slides it along this, I think of it like a rail. I've connected my center of dilation to the point that's getting dilated, and I slide that point along that rail until it gets to a place where its distance away from C is n, whatever n is, times the distance that it started away from C. So whatever r to C was, we multiply that in this case maybe by 1.5 if our scale factor is 1.5. We multiply that by 1.5 and we slide r along that rail until it's 1.5 times the distance away from C as compared to where it started. And every point's going to do that. X starts out some distance away from C. We slide it along this ray until it's 1.5 times as far away from C. And as a result, all the distances in our shape that got dilated end up being your scale factor times whatever they started out as being. One other thing that you're going to need to know, so those are the basic ideas of, those two things there that we just went over. Those are I think, kind of like the foundational properties of what a dilation is. They really kind of define what happens in a dilation. But there's a couple other things that we need to know. If we have something that's getting dilated, but it's on the center of dilation, right? So for instance, if there was a triangle here, triangle CXR. Let me just kind of sketch that out. Let's say we had triangle CXR, and we were dilating it by this scale factor of 1.5 centered at C. Well, C, one of the corners of that triangle, is on the center of dilation, which means that it actually won't move at all. It won't change its location. Our triangle would just kind of grow to be triangle CX prime, R prime. C and C prime would end up being in the same place. It's kind of like, if you remember back, we talked about reflections, and we talked about, let's say I have this line of reflection. I'm going to flip something over right there, and let's say the shape that I was flipping over that line looked like this. Well, this point here would go over to here. This point here would go right over to here. But this point right here wouldn't actually change its location because it's on the line of reflection, right? So our reflected image would look like that. It's kind of the same idea, that when you have a point that's on the center of dilation, it's actually not going to move when you perform the dilation. A couple other things that have to do with the scale factor. If that number n, the scale factor number, if that's bigger than 1, then we call the dilation an enlargement. Our shape is going to end up getting bigger. The segment, maybe we're dilating it at a segment, it's going to get longer. Maybe we're dilating a triangle, the triangle itself is going to start getting bigger. We are enlarging our pre-image if we have a scale factor bigger than 1. Now the scale factor has to be bigger than 0. We don't have negative scale factors, but if it's between 0 and 1, so like 0.5, 0.75, maybe it's a fraction like 2/3, then what happens there is we end up with a reduction. So the thing would get smaller, right? So, for instance, if I think about, let me get rid of my triangle that I drew there. Let's say I was going to dilate point R by a scale factor of 0.5, right? So I'm going to take this, I'm going to, instead of doing 1.5, which is kind of what I pretended this was doing to move it out here to R prime, let's say I was dilating that by 0.5. Well, that means that my new place for R is going to be half as far away from C as where it is right now. So the new location of R might be right around there. Let's go ahead and plot a point, maybe R prime prime. And the new location of X would be about half as far away from C, the center of dilation, as where it started. So my image of a dilation by a scale factor of 0.5 for this pre-image, the image would look about like this. Each of these is half as far away from C as where it started here. Again, and that's if my scale factor is equal to 0.5. The length of XR would be half of the length of X prime prime, R prime prime, this guy, would be half of this length here. So if the scale factor is bigger than 1, we're making our pre-image bigger, we're enlarging it. If it's between 0 and 1, then we are shrinking or reducing our pre-image. So just a couple more properties that we want to talk about. Dilations preserve angle measurement. So every angle in a dilation will end up being congruent to its original measurement, right? So if I look at the angle CRX and angle CR prime X prime, those two angles there end up being congruent. Same thing with CXR and CX prime R prime. These two angles would be congruent. They preserve angle measurement. But kind of by definition of what we talked about up here, they do not preserve segment lengths, right? When we dilate, we're going to change the length of segments. We're going to make them bigger or smaller. And so that's kind of the big difference between a dilation and those other transformations that we talked about, translations, rotations, and reflections. Those were all called rigid transformations because they preserved angle measurement and segment length. Dilations do not preserve they don't preserve segment length. They do preserve angle measurement, but not segment length, so they're not considered rigid transformations. Last thing about notation of dilations, if your notation is just like this, dn, where n is a scale factor, so maybe it says d2 or d1/4, what that's indicating is that the origin is the center of dilation, and that number that's down there is the scale factor. So in something like this, we would be enlarging our pre-image by a scale factor of 2. A dilation like this is a reduction with a scale factor of 1/4. But again, because it doesn't have comma and then a point, then we're centering our dilation at the origin. And we'll do some examples of that in our next video. But that's the basic idea behind dilations. We're going to take a point, we're going to connect our point to the center of dilation with a ray, and then we're going to slide that point along that ray so that it ends up at a distance away from the center that is the scale factor times the original distance that point was away from the center of dilation. So if our scale factor is 2, we're going to slide that point until it's twice as far away from the center as where it started.